Okay, so today we're going to talk about comparing the reactivity of metals and metal ions. So one of the properties that makes gold a precious metal is that it tends not to participate in chemical reactions. The data collected from the activity that we all just have completed indicates that silver too is not chemically reactive. At the atomic level, metal reactions occur when electrons are exchanged. So since gold and silver atoms tend not to be chemically reactive, these atoms must not readily lose their electrons to become metal ions. So by holding on to their electrons, gold and silver tend not to participate in chemical reactions like corrosion. Gold and silver are very stable metals. Silver ions, on the other hand, were the most reactive of the three metal ions tested in the previous investigation. Because of their tendency to react, you can conclude that silver ions must be able to gain electrons and use them in order to increase their tendency to react. You can conclude that silver must gain electrons and use them in order to increase stability. So there is a general tendency regarding the reactivity of metals and their metal ions. So the more stable a metal atom is, the more reactive its ion is. This trend makes sense because an atomic species naturally move to states that have greater stability. So if a metallic atom is more stable than a nearby metallic ion, the ions will tend to react to gain electrons to become metal atoms. So it is possible for a metal to be more stable in its ionic form than in its uncharged form. If this were the case, the metallic atoms would readily oxidize and easily undergo corrosion. So one particular metal, iron, for example, shows this trend in stability. So unless protected, iron readily corrodes. It is estimated that 20% of the iron produced each year is used to replace existing iron that has undergone corrosion. In the previous investigation, which of the three metals tested was the most reactive? Does the reactivity of this metal suggest that it is also more stable in its ionic form? Does this data you collect support this? And your observations should support a second general trend. So the more stable a metal ion is, the more reactive its metal is. Alright, so ordering reactivity, the activity series. So remember the general rules that govern the reactivity of metal atoms and their metallic ions. The more stable a metal atom is, the more reactive it is as an ion. And the more stable a metal ion is, the more reactive it is as a metal. So if you create a list that organizes metal ions from the most reactive to the least reactive, you end up creating a list that organizes metal atoms from least reactive to most reactive. So for example, here's the following table, where our most reactive metal ions are here, and the least reactive are here, but then the reverse is also true, where I've got my least reactive metals and my most reactive metals, okay? So this table can be adjusted to show the gaining of electron changes to metal ions to their other forms. The resulting is a table of reduction half reactions based on the reactivity of the atoms or ions in an activity series. So here again, it needs to, with the plus, it needs to gain one electron to become the metal here, okay? That's just what that's showing. So here's our activity series for metals and metal ions that you guys will be provided with for your tests and such. So the activity series for metals and metal ions is a valuable tool that can be used in a number of different ways. Like any other tool, it works best if you understand all of its features.
You need it in the office?
So comparing the relative reactivity of metal ions. So using the left side. So according to the listing on the left side of the activity series, Cu2 plus aqueous ion is more reactive than the zinc ion. This is indicated by my copper being farther down than my zinc. Okay? And this is consistent with the results of our investigation. Okay? And then we have our silver here that is actually higher than that, okay, which makes it more reactive as an ion. So the activity series for metals and metals ions, again, it's a valuable tool, okay? But if we look at just the metals using the right side of the series lists the metals in ascending order of reactivity. So metals that appear on the lower side of this, so or you've got our copper, our copper and our zinc, and our silver. Okay, these, show that my copper is actually up here. That copper is more reactive than silver and less reactive than zinc. Again, this matches our observations, okay? So the activity series, it will determine whether a reaction will occur. Okay, so perhaps the most useful feature of this table is determining whether a reaction will occur between a metal ion and a metal ion in solution. The reaction that occurs without the addition of external energy is called a spontaneous reaction. We have witnessed these in our investigation. When you place a strip of zinc metal into a solution containing silver ions, we also observed cases where no reaction occurred, where a strip of silver metal was placed in a solution of zinc ions. These reactions are called non-spontaneous reactions. So how is the activity series used to make these predictions? So the left side of the series compares the ability of metal ions to gain electrons, and the stronger the reduction reactions are written nearer to the top of the series. The right side of the series compares the ability of metal atoms to donate electrons. The stronger oxidization reactions are written closer to the bottom of this series. So a spontaneous reaction will occur if a metal ion has a stronger tendency to gain electrons than a metal atom. In this case, the reduction half reaction for the ion is found closer to the top of the chart. Since the reduction cannot occur without oxidization, the metal atom must have a stronger tendency to lose electrons than the metal ion, in the case where the oxidization half reaction for the metal is found closer to the bottom of the series. Okay, so what this is saying is that if our ions are higher up here, is found there, and our metal is found here, then we're going to have spontaneous. Where if our metal is found up here and our ion is found down here, then we will have a non-spontaneous. Okay? So a spontaneous reaction is a chemical reaction which occurs without the addition of external energy, and a non-spontaneous is one that occurs, that cannot occur without the addition of external energy. So it just shows there again what I kind of talked about before, where we must have, the tendency to go this way, or our ion above our metal, and if the reverse is true, then it's non-spontaneous. Okay. So, problem of zinc metal is placed in a solution containing Cu2+. Write a reduction and oxidization half reactions that describe this situation, and then locate them on the chart to determine whether it's spontaneous or not spontaneous. So, if I look here, my reduction. Okay, reduction, that's the gain of electrons. So I know that that's going to be from my ion to go to the metal. Okay, and then oxidization. That is the loss of electrons. Okay. So if we then were to look at, so this is A, if I was then to look at my activity series, I would notice that my reduction is above the oxidization reaction. Okay, so it will be spontaneous. And because of that, I know that copper ions would participate or precipitate out of the solution as copper metal, and my zinc metal would enter the solution to form zinc ions, and the precipitate would be visible.
Nolan Paul, you're needed in the office. Nolan Paul.
Okay, so if I go here for another example here, sorry, this is just here to show you that my copper here is above my zinc here. Okay, so that makes that possible. So if I look here at my second option here, it says that a piece of gold jewelry is dipped into an acid solution containing H+. Write a reduction and oxidization half reactions to describe the situation. So for A, I've got sorry. So my hydrogen ions go to gas. That's my reduction because it requires electrons, and then oxidization talks about the loss of electrons. Okay. Now if I'm to look over here, I would notice that gold, so to go that way, gold to go this way, is above my hydrogen, which is the one that goes that way. So means that for B, this is going to be a non-spontaneous. Okay, there we go. So, oxidization and reducing agents. So as we've seen, oxidization and reduction always occur together. This is because if one substance is going to gain electrons, another must lose electrons. So if we consider the following equation, in this reaction, silver gains electrons and the zinc loses them. In other words, the zinc acts as the reducing agent because it promotes the reduction of silver nitrate. Notice that reducing agent, zinc, lost the electrons, so the reducing agent is oxidized. So sometimes students find this confusing, so we need to focus on the word agent. Just as a travel agent makes it possible for other people to travel, the reducing agent makes it possible for something else to be reduced. Similar thinking can be applied to the process of oxidation. In the previous balanced chemical equation, silver nitrate is the oxidizing agent because it promotes the oxidization of zinc. Again, I'll focus on the word agent to remind you the terms describing what the substance does. Since the oxidizing agent, silver nitrate, is gaining electrons, it is being reduced. So a reducing agent is a substance that makes the reduction process possible by losing electrons, and the oxidizing agent is a substance that makes oxidization process possible by gaining electrons. Thank you guys so much for listening. I hope the background noise wasn't all of too distracting.